Let's take a look at an example problem involving impulse and change in angular momentum. Let's say that a person exerts a 2.5 Newton force perpendicular to a lazy Susan. A lazy Susan is sort of like a turntable that's often used in kitchens to store food items. The radius of the lazy Susan is 0.260 meters, and you apply that force at the edge of that lazy Susan for 0.150 seconds. Let's determine the final angular momentum of the lazy Susan if it starts from rest, assuming friction is negligible, and the final angular velocity of the lazy Susan, given that its mass is 4 kilograms and its moment of inertia can be assumed to be that of a disk. I will begin this problem by writing out my given information, including the symbols used to represent the variables each corresponds to. All right, I've gone ahead and drawn a diagram, like an aerial view, to represent the lazy Susan. I've indicated the force there perpendicular and labeled it 2.50 newtons. I know that the radius, or the distance away from the center of the lazy Susan that I am applying the force, is 0.260 meters. The time, little t there, is 0.150 seconds, and the initial angular velocity of the wheel is 0 radians per second because it is starting from rest. To help solve this problem, I've gone ahead and included an impulse table like from before when we solved problems involving linear momentum. This can be a helpful tool to isolate the variable that you are trying to solve for. And so in this case, I'll take a look at this table as I proceed to solve this problem. I know that the initial angular momentum of the lazy Susan before the torque was applied is going to be 0. This is because the initial angular momentum would be equal to, so this L, right, this would be L initial. That's going to be equal to I, the moment of inertia of the disk, multiplied by the initial angular velocity. And assuming that I doesn't change here, the moment of inertia of the disk is constant, so we don't need to keep track of I initial and I final. So we know that since the initial omega is 0, then this whole thing will just be 0. The wheel has no angular momentum before the torque is applied. Now, after the torque is applied, right, that final angular momentum is going to be equal to the moment of inertia of the lazy Susan multiplied by its final angular velocity. I don't know what omega final is, so I can't plug in here. But I do know something about the change in momentum, or the impulse, right? The change in angular momentum is going to be equal to the final minus the initial. And we know that that's also, right, our impulse is also equal to the torque multiplied by the time that torque was applied for. And so I can actually calculate my impulse right away. I know that the impulse is equal to the torque multiplied by the time period, and torque here is just the lever arm multiplied by F. And in this case, the force is completely perpendicular, so the angle between them will be 90 degrees, and I don't need to consider the angle between them then because the force is completely perpendicular. So that would be, again, multiplied by delta t. So the impulse, or the change in angular momentum, is just going to be the radius here. Because I'm applying the force all the way at the edge of the disk, the radius and the lever arm happen to be the same value. This will be 2.50 newtons, and this will be 0.150 seconds. And so the change in angular momentum, or delta L, is going to be equal to 0.0975 kilogram times meter squared per second. All right, and so I've solved for the impulse, but remember in part A, we're asked to solve for the final angular momentum of the lazy Susan. And so while we have delta L here, we don't know what LF is necessarily. However, we do know that they're very closely related, right? Delta L is equal to LF minus L initial, final angular momentum minus initial angular momentum. That's how any change in a quantity works. Well, if we know the change in momentum, and this is just 0, right, then the change in my angular momentum is just going to equal the final angular momentum, which makes sense, right? If it started with a momentum of 0 and we gave it some positive momentum, that's the momentum it's going to have after we're done applying that torque to it. So I know that my final angular momentum is just going to be that same 0.0975 kilogram times meter squared per second value. So there's part A. Now, how can we solve for the final angular velocity now that we know the final angular momentum? Well, that becomes as simple as plugging in our values for the final angular momentum and the moment of inertia into this equation. And so if I know that my final angular momentum is just the moment of inertia of the Lazy Susan multiplied by its final angular velocity, stands to reason that the final angular velocity will be that final angular momentum divided by I, the moment of inertia, if we rearrange for the final angular momentum, omega final. I don't know the moment of inertia in this case, but I can calculate it using the moment of inertia equation for a disk. The moment of inertia for a disk is going to be 1/2 times the mass times the radius squared. And in this case, the mass of the Lazy Susan was given to us as 4 kilograms. We would need that information. And the radius was 0.260 meters. And so I can actually solve for the moment of inertia in the disk. That will be 0.1352 kilogram times meter squared. All right, and now I'm going to go ahead and plug this value for my final angular momentum into the top of my equation for the angular velocity, and I'm going to plug this value into the bottom. And if I do that in my calculator, I will get that the final angular velocity is equal to 0.721 radians per second. All right, and so that's just a quick example of how we can use the relationship between our momentum equation and impulse, right, which relates a torque and a time period to angular momentum in order to solve for various quantities when we have a torque being applied to an object over a certain period of time, changing that object's angular momentum.